Welcome to Intelligent Systems, an introduction to artificial intelligence. In this lecture, we look deeper into how to use Tensorflow to classify MNIST digits. So far, we had three solutions. No, actually four. With 10% success rate, we could randomly predict labels because the groups were roughly balanced. So picking a digit randomly means 10% success rate. We implemented a simple solution in which we compared a given image against a template that was kind of randomly picked, a random 1, a random 5, a random 4. And we made a prediction for the digit of the template that has the smallest Euclidean distance to our given image. And that gave us 25%, not very good, but way above random. So that was interesting. Then we built the average template. So we simply superimposed all of the zeros, all of the ones, and so on, and took that as template. And that gave a staggering 80%. Now, why is that important? It's important to set a baseline. It's important to understand at what point our solution is really good. So comparing against the 10% random, any solution is really good. But with a simple averaging templates, we get already 80%. So any neural network approach should be way above 80%. So let's see how we can do. With a simple neural network that we implemented in Python, in the previous lecture, we got about 85%. If you train long enough and use all of the examples, you can even beef this up to 90%, but we don't do 100. In this week, in this lecture, we will use Tensorflow and we will make changes to the architecture of the network using convolutions, softmax, and dropout, and that will bring it up to 99%. If we look back at the bigger picture of what work focuses on when designing a neural network, we broke it down along this idea that a neural network is a function fw of x equals y, and we covered so far how to determine w and how to do so efficiently because we looked into forward propagation, back propagation, and that is in hand, so we get a check mark here. But how large does W have to be? Which structure for connectivity of the neurons do we want? How about the training data, the X and Y star? What quality is needed? How to represent all of this data? These are open points. And in the context of MNIST and our implementation in TensorFlow, we will discuss these points. So let's start with a representation of X. So in the original data, the images are 28 by 28 arrays with grayscale values, where 0 means black and 255 means white. And all of the values in between are also present. Now, in our TensorFlow implementation, we will convert this to floating point numbers between 0 and 1, simply by dividing all of the numbers by 255. So why are we doing that? One reason is that internal computations, such as the calculation of the weights, the activation function, all of these are float, so we might as well, right from the start, use floating point numbers. Then there is a problem of vanishing gradients, so that means we don't really want to have a neural network that is working on integer numbers, because the gradients can become very, very small and very large and so on, and we need to represent that, so that's floating point numbers. And finally, we may train a neural network on one task, apply it to another task, and so it's actually not such a bad idea to standardize all of the input and say the input must be a number between 0 and 1. Now, floating point numbers can be represented in different ways with different coverage and precision. We typically have 16-bit, 32-bit, and 64-bit, and that is the accuracy, and it implies also a bigger amount of memory that you need. So when you have 1 trillion parameters to train as in ChatGPT, then obviously it makes a huge difference whether you represent stuff in 64-bit or in 16-bit. And that decision must be taken. And anyway, floating point representation within a computer is a complex issue. And just to get a hang of it, try in Python print 0.1 plus 0.2 plus 0.3 with the brackets in the beginning and the brackets in the end. You will get two different results, namely 0.6 and 0.6, tons of a 0 and then a 1. Yeah, and that just reflects that internally the numbers are represented differently, and that does have an impact on calculations. Now let's move to y. So far we predicted a single output variable for y, and it had the value 0 to 9 to represent the different digits. We could not express uncertainty of our prediction. We could not say that we're really certain that this is a 5, or in another case that just this could be a 7, but it could also be a 1, but it's definitely not a 0. So now we introduce for each digit a category, and we learn probability distributions, which is called softmax. And so instead of having one output, we will now have 10 outputs. So it's not a single class problem, but a multi-class problem. And softmax is defined as follows. We have the weighted sum in the last layer. So essentially we build the sum here over the neurons I in the previous layer L-1. We take the weights WL from neuron I to neuron J times the output of neuron I in layer L-1, so that's this H over here. And we sum all of that up over all of these neurons in layer L-1. And that gives us the weighted sum AJL. And we can do this for the different categories K from 1 to K. That's the range of this J. And now we use this weighted sum in the following formula. We define Fk, where this lowercase k is now ranging over the classes. So in our case of the digits, 10 digits. And we build e to the power of ak divided by the sum over all classes j, e to the power of aj. And this means that Fk is between 0 and 1. And the sum over all classes of these Fk's is 1. So we have essentially defined a probability distribution with this vector F1 to Fk. And interestingly, this softmax function is the logistic function in k dimensions. Now you wonder, is it really? Let's do this for the binary softmax and see and prove that it is actually the logistic function. So the binary softmax we simplify now and don't use the indices I and j and so on, but let's make it simple. We just introduce two variables y and z, and then the binary softmax is e to the power of y divided by e to the power of y plus e to the power of z. And through a number of manipulations we will show that this is equal to logistic x, but you wonder, what is x? For those two variables, y and z, we introduce a new variable, which is the difference between y and z. And that means, in turn, that y is the sum of x and z. And that is what we can insert here into the formula. After inserting this, we can bring e to the power of z to the front and cross it out. And our formula has changed to e to the power of z, x divided by e to the power of x plus 1. Now, 1 is equal to e to the power of 0. And 0 is equal to x minus x. So we can move to this line in which we have replaced this 1 by e to the power of x minus x. Now we see e to the power of x here, here, and here. We can bring it to the front and cancel it out. And that means we have 1 divided by 1 plus e to the power of minus x. And that's exactly the formula of the logistic function. So softmax is a high-dimensional version of the logistic function, and the binary softmax is the logistic function. Now, so far we used the mean squared error, but now we have a situation in which we have multiple classes, and we want to predict this vector of multiple classes f1 to fk, these probabilities, to the probabilities of the known labels. And first of all, how are these probabilities defined? We know precisely which is the correct label. And that means this vector of y's is essentially consisting of zeros. Only the true digit gets a 1. Yeah? And such an encoding where everything is 0 but one value is 1 is called a one-hot encoding. It's kind of a standard terminology that you should know, one-hot encoding. So this vector of y's must be compared to this vector of f values. And in order to decide how dissimilar or similar they are, we introduce the concept of entropy and cross-entropy. Now, let's first get an intuitive understanding of what we want to measure. We want to see how disordered the sets are, how consistent our prediction is with the known labels. And we can actually apply this idea to consistency also within the predictions. So let's say here, for example, we've got a prediction where f is 1 and then 9 zeros. That means we're really certain that our prediction, our digit, is 0. So definitely 0. And the entropy for this, or the score that we give for this, should be low. Now, the opposite case to that would be if we cannot really determine at all what the image is about, and it could be anything. That means we give for all of the classes each 10%. That should give us a high value. There is nothing more inconsistent than that. And there is something in between where we say, okay, we can exclude a 4 and a 5, and we're definitely sure it's either a 7 or a 1. So that means 2 times 0.5, the rest 0. So that is quite good, but not perfect. So that should give us a low value. Now the function that gives us that is z multiplied with logarithm of z, and the negative, so that we bring this up to the positive. And essentially we get this over here, and when we now look at our 3 situations, definitely 0 means that we have minus 1 times log 1 plus 0 times log 0. Log 0 is not defined, but 0 is, so basically all of this becomes 0, and actually this becomes 0 too, because log 1 is 0. So overall 0, a low value, as we wanted. Now in the case of 0.1, we get 0.1 times log 0.1, and that amounts to 0.1 in total, and that means that in sum we have 1. Also perfect. And in this case, 0.5 times log 0.5 amounts to roughly 0.15. We got it twice, the other values were 0, so we got 0.3. So this definitely 1 or 7, a pretty low value here at 0.3, also good. So this concept is called entropy, and we sum this up over all of the values f that we have, as we showed here. So, and in this case, this is called entropy and not cross-entropy, because we were comparing here the f, or we were multiplying the fj with a logarithm of fj. Now, in the situation where we want to compare our prediction to the known labels, we turn this into cross-entropy, and we just replace this first f by a y, and that means now we have the comparison how similar the y's and the f's are. And now we know how consistent both of these are. As an error function, we average over this cross-entropy, and that gives us 1 divided by n, negative value here, and this first sum I ranges over all of the images, and the second sum j here ranges over all of the classes that we have, and then here yj times log fj. Quite interesting, we usually use this one-hot encoding. That means we have one true class for y, but in principle we could actually express also on our known labels uncertainty. Take this example here, where maybe we don't really want to commit and say this is a 1 or this is a 7, but rather we have 10 people judge, and 7 tell us it's a 1 and 3 tell us it's a 7, and that we want to have reflected in the labeling. So instead of the one-hot encoding, for such cases, we could in principle have this division and have 8 values 0 and 1 0.7 and 1 0.3. Now we have some insights into how to represent x, how to represent y star, the two labels. Now let's go and look into the architecture and how we're representing w. And what we're introducing is a bit of cheating, you could say, because we're leaving the fully connected layers where everything in layer k-1 is connected to everything in layer k, and we introduce some special operations like convolutions, which comes from image analysis, and pooling, which reduces the resolution of the data, and dropout, which simply removes data and increases the robustness of the networks. But let's look at them one by one. A convolution is a concept that is coming from image analysis and that is useful for edge detection. And it essentially brings information from the surroundings of a pixel to that one pixel. So conceptually, you see that over here, we have our image, and now we run this kernel, it's called, over this image, and we multiply the original values in the surrounding of a central pixel with weightings from the kernel, and we sum that all up, and that's the new value of our pixel. So if f is the original pixel, g is the convoluted pixel, w is the kernel of size a times b, then we can define formally this sum. So essentially we're visiting every pixel, and we're multiplying the value of that pixel times the weight from the kernel. We sum all of that up, and it gives us the new pixel. So that sounds pretty abstract, and you may wonder, why is that so useful? But you can see that in action over here. If this was the original data, clearly a 9, and you apply this kernel where the central pixel gets a weight of 4 and its neighbors get a value of -1, then this is essentially, this kernel is saying this pixel is standing out with respect to its neighbors. And what does this do? It gives us the outline of the 9. And that's quite beautiful because here the background, there the background remains untouched. And here the inside of the 9 is becoming pretty similar to the background. So we can really find the lines that define the outside and inside of this digit 9. Now the important thing is that for a neural network, we are not insisting on known kernels from image analysis that do some useful job, but instead we allow the neural network to create its own kernels. And we do so even by layering convolutions, by saying, okay, you can start off with some basic kernels that seem to be useful, and in a second layer you can build, based on these basic kernels, more advanced kernels. And the more complex the data will be, the more of such convolutional layers you will iterate. Now, the second technique is pooling, because we want to turn maybe our neural networks that has layer by layer increased in size, we want to boil it down and reduce it again. And for that, we're simply aggregating values. So here, for example, 2295, we're aggregating to 9 for max pooling, but we can also equally well build the average and put a 4.5 here. And we define the filter size. So for example, we take 2 by 2 values, so a square of 2 by 2, and the stride, that is the step size, how we iterate over the images. Yeah? So by the complete filter, we're moving to the next position. And what does this do? Practically, you can see here, for example, the 9 in high resolution, and after average pooling, you see the 9 is in low resolution. So although the images are the same size here, their resolution has decreased, and you can see that over here. But at that low resolution, you can still see that the 9 is clearly visible. And the third technique is dropout. A common problem in neural networks is overfitting. And that means the neural network learns the data that we use for training by heart. And that's, of course, a big problem when we show it novel data when the neural network is in use, because it may not have seen this data, and that means it cannot predict properly. The theoretical solution would be that we train multiple architecture, completely different approaches, and then we average over all of these different approaches. That's very complex and tedious and time-consuming and compute intensive, and therefore we want to have a practical alternative, and that is that during training we remove neurons randomly. Yeah? So that forces the neural network to build in redundancy and not solely rely on a certain neuron for a certain piece of information. In TensorFlow, we can introduce such a dropout layer and we can tell it how much of the neurons in that layer to drop. So we have covered representation of X, Y star, and W. Now let's turn to the question how much data we need. If you look at textbooks, then you get a rule of thumb that 5 times or maybe 10 times the number of dimensions is a good size of training data. For MNIST, that is okay. So for example, 5 times 28 by 28 is far less than the 60,000. 10 times would be a little bit above the 60,000, so we seem to be all right. But you see right away that if you have 1 million or 1 trillion dimensions, then of course you would need a lot of images. So the main concept here is that you relate the amount of training data to the number of dimensions that you're dealing with to represent your problem. And the number of dimension is generally a problem because in high dimensional space, things do not really work as we are used to in low dimensional space. And there is, for example, the problem of the curse of dimensionality, which essentially says that if you specify your problem at a very low resolution, you will have poor results. So as you increase the number of dimensions to represent your problem, you will get improvements, but only up to a certain point. At some point, performance starts decreasing as you increase more and more dimensions. Yeah, so obviously, if you try to solve the MNIST classification problem with, let's say, 2 by 2 pixels, you will definitely fail. 4 by 4, you will fail, but maybe you can do already something. With 10 by 10, it's pretty clear you should be able to do something. 28 by 28, we have seen there are good solutions. You could imagine that increasing this a little bit will maybe still improve results, but if we do 1000 by 1000 or 1 million by 1 million pixels, it's actually deteriorating. Because high dimensional space is behaving strangely and counterintuitive. Just as an example, imagine that you take a circle and a square, and you have both of the same radius or the same diameter, and that means the circle is perfectly fitting into the square. Then you move now from this 2D case to the 3D case in which you have a sphere and a cube. And again, you make the diameter the same for both, and you can place the sphere perfectly into the cube. And the volume in the 3D case and the area in the 2D case between the two roughly correlate. They're not that different. But as you increase the dimensions, the ratio between the high-dimensional sphere and the high-dimensional cube converges to 0. And that is not really directly intuitive. And if you, for example, place in a high-dimensional space Euclidean points with a uniform distribution, then the Euclidean distances between these points become very similar to each other. In fact, it can be shown that the center of the random points has a mean of the number of dimensions d divided by 3 and a variance of 4d divided by 45. So the exact values don't matter here, but what matters is that with the increase of dimensions, this space is behaving counterintuitive. So now let's look further into the MNIST with TensorFlow, and we have covered now the structure of connectivity of the neurons with the different techniques of convolutions and pooling and dropout. How large W has to be, we will get to now as we're actually building the layers, the representation we have dealt with, and also the amount of data that we roughly need. So check marks everywhere so we can get going. And here are code snippets of the code that you're presented with in the labs. And these are the main code lines that are important to explain. And let's go through them one by one. Talking of representation, this is the line over here where we convert the training data from integer values to floating point with 32-bit precision. We turn the values y, the labels, from 0 to 9 to categorical data to 10 different classes with this command to categorical. Then we start by defining our model, which is sequential, in contrast to other neural networks that are non-sequential, and our input shape are 28 by 28 pixels, and since they're grayscale, we have a 1 here. If we had RGB values, this would be 3. And with conv2d and the command add on the model, we introduce the first convolutional layer that has 32 kernels of a size 3 by 3 and an activation function of ReLU. Then we introduce a second convolutional layer of 64 kernels. After that, we're reducing the size of the data and apply max pooling with a pool size of 2 by 2. Then we drop out a quarter of the neurons. Then we turn the matrix data structure that we have been working with so far and turn it into a vector. And this vector we then reduce to 128 neurons. So we introduce a fully connected layer, that's the keyword dense, with 128 neurons, an activation function against ReLU. Then we drop again 50% of the neurons, and finally we have a dense layer of 10 neurons, these are our 10 classes, and as our activation function softmax. Then we define the loss function and we use the cross-entropy as we've discussed it. And as the step size, we do not have a fixed value of, say, alpha 0.1, but instead we use an optimizer called Adam. So Adam is basically doing hard work for us because Adam is optimizing different step sizes for different dimensions during different epochs, different adjustments. So we don't really have to fiddle around with this alpha value ourselves. And then finally, we apply the fit method, and that carries out the training. We provide here the training examples and the training labels. We say that batch size is 64, so after 64 examples, the weights are updated. We run it overall for 5 epochs, so through the different batches, we will iterate 5 times through all of the examples, and then we validate on the test data for X and Y. And this setup achieves an accuracy of 99%, so we nearly do perfectly. And it creates roughly 1 million weights. So you see that simple problem and those few lines of code create already quite a sizable problem. Now, let's look at 2 detailed questions. Why are we introducing 2 convolutional layers? Why not 3? Why not just 1? And why are we using the ReLU function and not tangents hyperbolicus and logistic function? So let's stick with the convolutional layers first. In the first layer of the 32 kernels, we allow the neural network to create basic patterns like edge detection that I showed in the example. And in the second layer, these basic patterns like edges, they can be composed and more complex patterns can be derived, like circles and stuff, so that we can capture an 8 or a 9. A third layer is not needed because we were already at 99%. The MNIST dataset is not that complex. But for ImageNet with cats and dogs and container ships and so on, and 3 channels rather than just grayscale and so on, we may need even more complex patterns and more convolutional layers. But for this specific problem, after 2 layers is good enough. Now, why is ReLU used and not tangents hyperbolicus and logistic? So a big problem in neural networks is the so-called vanishing gradients problem. So as we're moving in backpropagation from the last layer to the first layer, the gradients by which we adjust the weights, they get smaller and smaller and smaller, but they don't completely disappear. They don't become 0. And as they get smaller and smaller and smaller, the changes of the weights get negligible. And that means we're doing heavy computation, but it doesn't really carry over to substantial change. And that is a problem that is appearing more frequently with the logistic function and with tangents hyperbolicus, and it's less frequent with ReLU. And the reason why it's less frequent with ReLU is that ReLU is very rigorous. It's saying that negative values get rigorously mapped to 0, no matter whether it's a small negative value or a really big one. they get mapped to 0. And the positive values get mapped to identity. That means the range of ReLU is from 0 to infinity, whereas for tangents and logistic it's a much smaller range. And then ReLU is also much easier to compute than logistic and tangents H, and since we're using it so frequently, that really makes a difference, because ReLU is just the maximum out of 0 and the output of the neuron. So 99% accuracy, and here are examples of those examples that could not be classified properly. So you can see right away that despite this great success rate, the misclassifications by eye, you can judge they can be done, because in the human eye you clearly see this is a 4, this is a 1, this is a 6, because we approach the problem differently in our visual conception. But you also see that there are some examples where it's clear it is really tricky. So for example, this over here being interpreted as a 7 instead of a 2, that's very clearly a very tricky case. Or this 7 over here, which the neural network thought is a 9. Okay, so we've done it. We have achieved a pretty good solution with really just 20, 30 lines of Python code using the Tensorflow library. So with that code, you can play now, and you can ask questions like, what changes if I move from 32-bit precision to 16-bit or to 64-bit? What happens if I vary the number of kernels, or if I drop the second convolution layer or introduce a third one? What happens if I vary the dropout rate, or if I change the pool size? So you can play with all of that and see how the performance of the neural network changes. And most important, probably, what happens if you decrease the the size of the training data. Just train on 1,000 or on 10,000 results rather than all of the 60,000. However, there are some more advanced changes we can do, and that is, let's change the task that we're actually learning, and let's change the architecture. And that brings us to a really, very nice part of this lecture, because we will now look into autoencoders, variational autoencoders, and embeddings. And that is really the key techniques that are conceptually behind efforts like ChatGPT, like generative AI for creating images, and so on. So let's vary our task. So we start out with something really counterintuitive and we say, well, what happens if we don't make the task classifying digits, but instead we make the task classifying, repredicting images. So this 9 should be predicted into this 9, where you say, well, that is easy to do. We can just transfer the input from here to the output directly. Then it's a pointless task, isn't it? True, that would be a pointless task, but we're making it difficult for the neural network because we're insisting that here's a bottleneck and that you cannot pass through the pixel directly. You must pass through the bottleneck. And we make that bottleneck low dimensional. Now, we know that some dimension reduction is no problem. All of the images have a black outer layer, so that doesn't really carry much information. But how far can we push it? And you will see that we can push it actually quite far to 7 by 7 pixels from 28 by 28 and still be able to recover the full image. So that makes this a very interesting task. And we can implement this by creating our input layer of 28 by 28 pixels, then a convolutional layer, pooling, convolutional, and another time pooling. And that way we have reduced the data, the matrix, and we have introduced our image of size 7 by 7. So we have heavily reduced our dimensions, and we have created a significant bottleneck. And then we invert the convolution with a layer of conv2d transpose. And that blows up the 7 by 7 to 14 by 14, a second time 28 by 28, and here we stay with the 28 by 28. And overall, we have used 28,000 parameters, and we have implemented exactly this structure. And that is what it's looking like in TensorFlow, code. So here, 32 kernels, pooling with 2 by 2, here with 2 by 2 again, and then the transpose with 32 kernels, and over here a convolution of 3 by 3. Atom is being used and cross-entropy as loss. So this is not a super complex network. We're still at 20-30 lines of code for this autoencoder. And see what it does. So despite the bottleneck that we have introduced, it is able to perfectly recreate the images. Now you wonder, what the hell? Why is that useful? Because of this. We can insert heavily deteriorated images of digits with a lot of noise, and our autoencoder is removing this noise. And I think that is pretty impressive, and it has many practical applications. So 2 of them you can see on this slide. These were 2 papers that were coming from groups here in Dresden, which worked on microscopy data. And the microscopy data is here. Some Chinese characters are over there, and some photos over here for their technique. This is the noisy original image. This is the ground truth. And all of these are kind of noise removed images with autoencoders. And I think you can best see that in this image by the Chinese characters, which are really quite deteriorated here at the beginning. They can be recovered quite nicely when compared to the ground truth. So these autoencoders and noise reduction is really a very, very nice application, but we can do more. And instead of having as this bottleneck an image, or not really an image, but a low dimensional representation of the image, we have a probability distribution. So we try to say that we say, okay, you have a bunch of neurons here, and these neurons learn the mean and the variance of a Gaussian distribution. And from this distribution, we can sample. And then we can blow up this latent representation and recreate a new image that was actually not really present in our training data. And that is called a variational autoencoder, and that is the basis for generative AI as you know it in many of the applications of image generation or also of textual generation. And you can see that here in the TensorFlow architecture, and if you go to this link, you can also see a tutorial that gives you the code for this. So after the input layer, a convolution, another convolution, we're at 7 by 7, then we flatten the network, 3,000 parameters, have a dense, fully connected to 16 parameters, and on these 16 neurons, or on the shape of 16, we apply a layer that basically generates the mean of the distribution, the variance of the distribution, and that samples from this distribution. And with the sampled latent representation, we then recreate and decode the image by essentially reversing the process, having a dense layer, reshaping it from a vector into a matrix, then applying the transpose convolution, another transpose convolution, and another transpose convolution. And that structure recreates an image, and samplings from that space that we recreate this way, you can see over here, and you see really quite beautiful how these images nicely sample the space of digits. So here, lots of ones, this slowly changes into 7s over there, something between 4s and 9s, 8s over here, 5s over there, 2 over here. These could also be 9s and so on. So we have created these images. These images were not there. They were created from a statistical representation that was low dimensional in a latent space from which we were sampling and undoing the dimension reduction steps of the convolutional layers of the encoding in this decoding process. And a third application, besides image generation, are these embeddings. So now we're back to the to the first example, no probability distribution, but again, just a vector. And this vector is called an embedding. And what we're doing now is that we're saying, well, originally when this embedding is created, there is a decoder that helps creating it, but then we actually remove the decoder and we just provide to people these embeddings. Now, why is that interesting? Because the encoder is absolutely massive. Because the input was not 60,000 MNIST digit, but the input was billions and billions and billions of online photographs, or billions of amino acid sequences that can be scraped together from public databases. And the processing for this massive encoder was a very, very large computation that requires specialized hardware, high performance computing, large storage that an average user, an average programmer, or even an institute would not have available. However, in the end, all of this big data is turned into a low-dimensional representation. And that low-dimensional latent representation, that is usable by other people. And so these small players, like individuals, programmers, they can take these embeddings and then they have maybe a small-scale task that is just having a bunch of examples and is training a small neural network for some very specialized task. Now, what is the advantage of all of this? Why should we be doing this? The reason why you should be doing this is that for the small player, the embedding leads to much, much better results than the original data does. Why is that the case? Because the embedding reflects your small amount of data in the context of a big amount of data that is out there in the world. And surprisingly, that leads to really much, much better learning results. And one example of this I mentioned already earlier, that is now widely spread in bioinformatics. So instead of representing amino acid sequences by amino acid sequences, you can work with their embeddings. There are websites with databases where you can download these embeddings for all proteins that you want to work with. And the embeddings are, for many, many machine learning applications, much better representations than the original amino acid sequence. And the reason is that while I'll be just working with maybe 10,000 amino acid sequences, the embedding implicitly holds the information over billions of amino acid sequences. And it's somehow implicitly encoded. I don't really know why, but for the neural network that I train on my small data set with only maybe 10,000 of these embeddings, it manages to make use of this information and solve my machine learning task in a better way. And there are tons and tons of examples that over and over show how these embeddings are very, very good representations. Okay, so that basically closes, I think, a very exciting part of this lecture: autoencoders, variational autoencoders, and embeddings. These are really now cutting-edge approaches in your network research, and I think on this MNIST example and with this background, you should have a good understanding how, in principle, these things are working. And you should understand some of the excitement, but you should also be aware of what the limits are and what the problems are in this. Now, so far we have mostly focused on images, and of course the counterpart to images is text, and I'll just throw in here a couple of buzzwords that you have heard them. We don't touch this at this stage in more detail. And in the same way as you had massive new developments in image analysis with neural networks, the same is true for text. And text is pretty different to images because it is sequential and there are dependencies. There is an order in which you write and put words next to each other. And special architectures of neural networks were created to deal with these dependencies. And a big class of neural networks are called recurrent neural networks, and they have within the neuron's internal state, and they are able to, for example, in a sequence, to take into account the previous word, for example, and the calculations that were done in the previous step. And a particular class of recurrent neural networks are so-called long short-term memory, LSTMs. and they have all in common that they keep internal state, and ultimately this led to the development of so-called transformer architectures. They're called transformers because they transform one sequence of words to another sequence of words, and the starting point for this was machine translation, translating English into German or Arabic or Chinese, and a key mechanism was so-called attention, which allows the neural network to focus on specific aspects. There's a famous paper that has many, many citations and was very influential called Attention is Everything You Need. And in this context, there are a couple of buzzwords that I just want to mention here that you have heard them. One thing is how to represent your textual data. And instead of just putting down letters or by saying, okay, I somehow define what a word is, you typically use techniques like byte encoding, in which you just say, I don't care about letters or words. I want to have the most compact representation that allows me to represent these vast amounts of textual data as vectors, but not necessarily as letters. And if I find that frequently a certain combination of letters is going together, that becomes an own digit, if you will, an own number. And a technique, an algorithm to do so that is also used in compression of data files is so-called byte encoding. There are others that are used as well, but byte encoding is the standard. And then, as I said, an early technique from machine translation was sequence to sequence. Another buzzword is word to vec, which tried to represent a word as a high-dimensional vector, but only with a handful of dimensions, really, and represent in these dimensions the context that this word is being frequently used in. GLAF is a similar approach as word to vec, and these led to, in I think 2017, it was to really a milestone paper by Google, which was called BERT, and which was a milestone in that it created what was called a large language model, and that was essentially this statistical representation of huge amounts of text that you could then deploy for downstream tasks in natural language processing that made it much more efficient. So BERT was really the first earthquake in all of these developments, and it was building on these ideas that were developed in GLAF, word to vec, and sec2sec. And then GPT, as you know it from ChatGPT, is a build again on BERT, and all of these implement transformer architectures. And again, this slide is only here as an advertisement. We will not cover this in detail here in this lecture. Now, in the last slides for this video, let's look into limits of neural networks, because it's pretty impressive what we have seen so far, but of course there are also problems and there are limits to what neural networks can do. And one very, very difficult question, probably the most difficult aspect of all, is how to actually select representative data. And we've seen that in the MNIST case already, that you could say, well, it's clearly visible, this is not German. This data was not generated in Germany, because Germans typically write one not as one line. They write the one as a line with a hook at the top. And because they write the one with a hook at the top, it's important that you write the 7 differently. Whereas in the US and Britain, the 7 is typically written as 1 stroke. In Germany, we often write it as 2 strokes. So basically the basic shape, and then there's a line in the middle. So anyway, how to create representative data, but the MNIST dataset is not representative of Germany, that much you can say. And there are spectacular examples where non-representative data or non-representative training data and training tasks led to spectacular fails. And one of the most spectacular ones was when Google was under really big pressure by ChatGPT, and in February 2024 they released Gemini, saying, okay, look, we can do the same, we're as good as ChatGPT and we can create images. Then some journalists asked the system to show a picture of German soldiers in 1943. Now Google, because they try to be particularly representative and include diversity in their model, wanted to be very diverse when it came to general soldiers. And the picture that was presented by the system is this one over here, right? And shows an Asian-looking lady, a black male, and a female. So it's basically really nicely balanced. Two women, two men, different ethnicities. But sorry, very, very bad. That is not representative of German soldiers in 1943. Similar, you can turn it, of course, easily around. I just went to ChatGPT and asked it, draw a human being. And look at what it comes up with. This is clearly biased. You know, it's a black male. Why did it pick a man and not a woman? To me, yeah, this looks clearly white. You know, is this really representative of humanity? But of course, this is an extremely different problem, and really a nice discussion on this you can find on the wiki article about the Pioneer 10 plaquette. This is from the 70s when humanity sent a spacecraft into outer space, and they scratched onto the outside of the spaceship drawings of humans, so that if some aliens may find this spaceship, that they have an impression of who's living on Earth. And this is what the plaquette looks like, and you see here a male and a female. So interestingly, they could not agree on one single representative for the species human, but they said, no, look, we're roughly 50-50, and that means we must have a man and a woman. And they made big effort to create this outline shape of this male and this female, so that every ethnicity would think that it's their ethnicity. So whites would think, oh, this is a white. Asians would think it's white. I don't know whether it's true, because for me they look clearly white, but apparently they try to make some effort to make it beyond ethnicity. And nonetheless, you see it's really a huge problem to create something representative. And in the case like the representative human being, I think you cannot have one. You need at least two. So it's difficult, and that means neural networks are biased, full stop. And you have to be aware of what the bias is, and you have to be aware of what the bias means for what the neural network does. And that's not the responsibility of the neural network. That's the responsibility of the people who create the neural network and who use the neural network. Neural networks are not robust. For any analysis, this has nothing to do with neural networks really. You want to have the property that a small change in the data leads only to a small change in the results. And here you can find striking examples that is violated by neural networks. So this picture here on the left is classified as a dog, but then if you add this noise, which to the human eye is not visible, it creates the same image of the dog, is labeled as an ostrich. And it gets even worse. In this picture, the banana is not changed, just something else is placed next to the banana, and the prediction changes from banana to toaster. Yeah? So neural networks maybe are largely robust, but not entirely robust. And you can always find these attacks where you make a minuscule change and the neural networks gets it spectacularly wrong. Neural networks cannot really reason, and that is now really under heavy study as companies also want to push the forefront of what neural networks can do. But there is a full paper which you can find on archives published this year, which investigates many language models, including ChatGPT, and it gives us this simple task. Alice has M brothers, and she also has M sisters. How many sisters does Alice's brother have? Every child can answer this question, and I basically instantiate this N and M. They give it different combinations of numbers, and generally the language models, ChatGPT, cannot really answer this question correctly. And finally, I've mentioned it already, overfitting. Neural networks may suffer from the problem of learning the training data by heart. There's something you can do about this as you observe the accuracy as it's increasing along the epochs, and if the training accuracy and the validation accuracy are pretty similar, if they're behaving pretty similar over the epochs, then there's little overfitting. But if we see that our validation data set, the accuracy is not really going that far up, and across over epochs is even going down, then this is an indication that there is strong overfitting. And that essentially means our neural network has learned the data by heart. And this problem of training and test data is particularly difficult because we have to ensure that there is no leakage from training to test data. How can we really ensure that the test data is not informed about the training data, that there is not a connection between the two? And that is more difficult than you think. So, for example, we once combined 3 systems with their predictions and created kind of a meta server with a meta prediction. And that was much better than the 3 individual systems. But what we didn't know was how were these 3 individual systems trained. And chances were pretty high that what we evaluated our meta system on, that data was maybe seen already by the individual systems over which we did not have control. Right, so that is clearly a case where there may have been some data leakage, and that is the reason why we observed so good performance, and not because the integration of the 3 systems was so good. So, take-home message for today's video, pretty much. You should understand why we have softmax, what softmax is, why we have cross-entropy and how it works. You should understand in the architecture of the neural networks what convolutions are, pooling and dropout. You should understand the concept and also have a basic understanding how to implement autoencoders, variational autoencoders and embeddings. And you should be aware of the limits of neural networks with bias, robustness, reasoning and overfitting. And most of all, you should be able to implement a neural network in Tensorflow if guided and using basically the insights that you get from the existing code.